Hello students, in today's class I am going to discuss about Bohr's atomic model. This is the topic from chapter 26. In yesterday's class we have discussed about Rutherford's atomic model. So today is the discussion about Bohr's atomic model. Now in 1913, Scientist Professor Niels Bohr removed the difficulties of Rutherford atomic model by the application of Planck's quantum theory. For this, he proposed the following three postulates. So the first postulate proposed by Niels Bohr was electron can revolve only in those orbits in which their angular momentum is integral multiple of h by 2 pi. Integral multiple means any number multiplying with h by 2 pi, where h is known as Planck's constant. So h is a constant. So he told that electrons cannot revolve in any orbit. It can only revolve in such orbits whose angular momentum is equals to n multiplied by h by 2 pi, where n is integer such as 1, 2, 3, which is the orbit or which these numbers are known as principal quantum number. Principal quantum number. So he told that angular momentum should be this much, then only those electrons can revolve in certain orbits. And this angular momentum, the formula for angular momentum which you have studied is mvr. M stands for mass, v for velocity, r for the radius, is equals to nh by 2 pi. This equation is also known as Bohr's quantization condition. It is also known as Bohr's quantization condition. This is the first one. Thus, according to Bohr's atomic model, electron can revolve only in certain discrete orbits of definite radii, not in all. These are called stable orbits. So certain electrons can revolve only on certain orbits, which are known as stable orbits. This was the first one. Second postulate of Bohr's atomic theory was, while revolving in stable orbit, the electron do not radiate energy in spite of their acceleration towards the center of the orbit. So whenever electron revolves around the orbit, whenever it revolves, it does not radiate energy. Hence, the atoms remain stable in the orbit and is said to exist in a stationary state. So it can only revolve in their certain orbits. It does not radiate energy. So there is no loss of energy of the electrons. This is the second one. So for second one, what you can write is electrons do not radiate energy. Third one is when an electron receives energy from outside. So in the same situation, when an electron receives energy from outside, then what happens is the electron will jump to higher orbit. So if there is an electron in the first orbit, if it receives electron energy from outside, then it jumps to higher orbit. Okay, it jumps to higher orbit. This state is called the excited state. This is the excited state of this particular electron. The electron in the higher orbit stays only for 10 to the power minus 8 second and it returns back to its own orbit. While returning back to its own orbit, at that time only it radiates energy in the form of electromagnetic EM waves. So it radiates energy only when it jumps from higher to lower orbit. So the frequency of radiation is nu. The frequency is nu. Suppose energy at higher orbit is E2 and energy at lower orbit is E1. Then E2 minus E1 is equals to, whenever it jumps from higher to lower orbit, it radiates energy or electromagnetic waves of frequency nu, where h is the Planck's constant. So from here, nu is equals to E2 minus E1 divided by h. Okay. Now this condition of Bohr's, where we get the formula for frequency, is known as Bohr's frequency condition. Bohr's frequency condition. So these are the three postulates given by the Bohr's atomic model, which describes the formation of atom properly. With that, we'll start with Bohr's theory of hydrogen-like atom. A hydrogen-like atom consists of a tiny positively charged nucleus, a very small nucleus having charge plus Ze. Charge of the nucleus is plus, Z is the number of proton or the atomic number. It is very tiny nucleus and a single electron revolving in a stable orbit around the nucleus. So this type of atom, a very tiny nucleus and a single electron, is known as hydrogen-like atom, which is very similar to hydrogen, or which is as equal as hydrogen. So this electron has got as charge E. Okay, E is the charge, m is the mass of the electron, and V, it is moving or revolving with velocity v. So V is the velocity of this particular electron, and R be the radius of orbit. The positive charge on the nucleus is Ze. So charge on nucleus is plus Ze, where Z is the atomic number. In case of hydrogen-like atom or hydrogen, Z will be 1. So for hydrogen, Z is equals to 1. Atomic number is 1. Now, whenever an electron revolves around, it is acted by a centripetal force, whereas whenever there are two charges, there is electrostatic force of attraction in between. So whenever centripetal force and electrostatic force is perfectly balanced, this electron will be able to revolve around the nucleus. So for that, two forces has to be balanced. That is centripetal force and electrostatic force. The formula for centripetal force is mv squared divided by r, mass velocity squared divided by radius. Electrostatic is 1 by 4 pi epsilon naught q1 q2. Over here q1 is Ze, q2 is E divided by r square. Now from here, if you solve this, and this r will get cancelled. So this can be written as mv square is equals to Ze square divided by 4 pi epsilon naught r. So this is equation number 1. Now from the first postulate, from Bohr's first postulate, what we know is angular momentum is equals to integral multiple of h by 2 pi, where n is the principal quantum number, or n is equals to 1, 2, 3, depending upon the number of orbits. Now let this be equation number 2. Now squaring equation 2. When we square this equation, what we get is m square v square r square is equals to n square h square divided by 2 square is 4 pi square. So from this, if we keep r this side, r square this side, and taking rest everything towards the other side, so what we get is r square is equals to n square h square divided by m square v square r square, 4 pi is also there, 4 pi square. So this is what you get. Now dividing this equation by equation number 1. Okay, we're dividing this equation by equation number 1 over here. Okay, before dividing, I'll just cut this last step, okay, because first of all we need to divide, then only we'll arrange it properly. So now dividing this equation by equation number, we're dividing this equation by equation number 1 over here. So this is how I can write. Okay, so from here 1m, this will get cancelled, v square will get cancelled. So this side 1 pi will get cancelled, 4 and 4 will get cancelled, rest 1 r will also get cancelled, this r and this r will also get cancelled. I'll just rearrange this. So from here what we get is 1m is there, so m r square is equals to n square h square, taking this to factor at the top, epsilon naught r divided by pi z is there, z e square. So now 1r and this r will get cancelled, taking this m towards the other side, r is equals to n square h square epsilon naught divided by pi m z e square. This is what we get at the end. Let us mark this at equation number 3. Now this is the equation for radius or radii of permitted orbits. Now from here what we can see is r is directly proportional to n square. So if n is equals to 1, 2, 3, it follows that the radii of the permitted orbit increases by the ratio, then r will be 1, 4, 9, 16, like this. So this will be the permitted orbits if this is the principal quantum number. Now from here we'll also talk about Bohr's or Bohr's radius. Bohr's radius. Now the radius of the first orbit for n is equals to 1, and for hydrogen z is equals to 1. Okay, atomic number is 1. If you use in this equation, if you put in this equation, we get r is equals to, if this is 1, then no need to write h square epsilon naught divided by pi m e square. So this is for r1, the first radius of the atom or hydrogen-like atom. This is called the Bohr's radius. This equation is known as the Bohr's radius. And after putting all the values of this constant, all these are constant, after putting all the values, we get R1 is equals to 0.53 angstrom. Now since R2 for R2, you can directly multiply it with this number, that is 4. It becomes 4 into 0.53. For R3 it is 9 multiplied by 0.53 angstrom. This is how the size of the radius of the orbit or the atom increases one by one. With that, the next is velocity of electron in a stationary orbit. Now from equation number 2, okay, from equation 2 is mvr is equals to nh by twice pi. From this equation, v is equals to nh 2 pi m into r. This is your v. Now putting the value of r from equation 3, so whenever we put the value of r from equation 3, what we get is, you can just put and find the value to the derivation. Just put the value of r from equation number 3. We get v is equals to ze square divided by 2h epsilon naught 1 by n. This is what we get. So from here, what we can conclude is velocity is inversely proportional to the number of orbit, or the principal quantum number. This shows that the velocity of the electron is maximum for the lowest orbit. For n is equals to 1, velocity will be maximum for n is equals to 1. As we go on increasing the orbit, if you go to the higher orbits, the velocity of the electron decreases. So for initial first orbit, velocity is maximum. So if you keep on increasing the orbit, velocity of this orbits will keep on decreasing, as it is inversely proportional. Now velocity of electron for n is equals to 1, v1. If you put 1 over here, v1 is for hydrogen-like atom, okay? For n is equals to 1 and for z is equals to 1. This is for hydrogen-like atom. You can write v1 is equals to e square by 2h epsilon naught. After putting in this particular equation, we get e square by 2h epsilon naught. This is for v1. The value of v1, if you put all the values of this constant, we get 2.19 into 10 to the power 16 meter per second. With this, we also have to find the energy of electron in a stationary orbit, or energy of an electron in a particular orbit. The energy E of an electron in an orbit is the sum of kinetic energy and potential energy. So it is sum of K plus U, kinetic and potential. So kinetic energy is half mv square, which is equals to, if you put the value of V from this equation over here, then it becomes half m. Let us put the value of V, that is ze, everything is square, so this becomes okay, this equation, okay, I'm not putting the value of V from over here. It's actually the same equation, that is equation number 1. So I'm putting the value of this one from equation number 1. So K is equals to half mv square. Putting the value of V from equation 1, K becomes half m. Equation number 1 is mv square is equals to ze square. So in place of mv square, we can directly write ze square by 4 pi epsilon naught into r. Or this can be written as K is equals to ze square divided by 8. 2 into 4 is 8 pi epsilon naught r. This is kinetic energy. Now the potential energy of the electron in an orbit of radius r due to electrostatic attraction by the nucleus is given as potential energy U is equals to 1 by 4 pi epsilon naught Q1 Q2, that is Ze, Q2 is E, that is minus E, electron, this is proton, this is electron. Now if you solve this, you get minus 1 by 4 pi epsilon naught Ze square divided by R. This is the potential energy. Now if you add this, E is equals to K plus U. So if you add this, ZE square divided by 8 pi epsilon naught R plus, now over here it is minus, so minus 1 by, or directly you can write ZE square 4 pi epsilon naught R. Now from here what we can take common is, we can take everything common apart from 1 by 8 and 1 by 4. So from here we take everything common, that is E square divided by, Z square divided by pi epsilon naught R. Inside the bracket we write 1 by 8 minus 1 by 4. If you solve this separately, if you solve this part, we get minus 1 by 8. So the value of E becomes minus 1 by, not 1 by, ZE square by 8 pi epsilon naught R. This is what we get. Now substituting the value of R from equation 3. Okay, substituting the value of R from equation 3, we can write E is equals to okay, just put the value of R from equation number 3. This becomes M is equals to minus, E is equals to minus M Z square e to the power 4 divided by 8 epsilon naught square H square inside the bracket 1 by N square. So this is the energy of an revolving electron, where N is the principal quantum number. Okay, this is the expression of energy of the electron in the nth orbit. So this is the energy of an electron in any nth orbit. Now suppose in an excited atom, an electron jumps from higher orbit. If there is a higher orbit, E2, electron jumps from higher orbit to lower orbit, E1. So let us see what will be the difference of energy, that is E2 minus E1 is equals to, if it jumps from N2 to the orbit N1. So what happens over here? This becomes minus mz square e to the power 4 divided by 8 epsilon naught square h square 1 by n. For E2 it will be N2 square, okay, minus for E1 again we need to write the same thing, so minus and minus plus mz square e to the power 4 divided by 8 epsilon naught square h square 1 by n1 square. After taking common and rearranging, this becomes E2 minus E1 is equals to, let us take this two factor common, as this has got minus, that is why I will write this 1 by n1 at the first. So mz square e to the power 4 divided by 8 epsilon naught square h square is common. Inside the bracket, as this has minus, I am writing this in the second, so it will be 1 by n1 square minus 1 by n2 square. This is the difference of energy in two orbits. Now according to Bohr's third postulate, from third postulate, it was frequency of the emitted radiation, that is nu is equals to E2 minus E1 divided by h. Now putting the value of E2 minus E1 in this particular equation, nu is equals to mz square e to the power 4 divided by 8 epsilon naught square h square. There is this h also, so it becomes h cube inside the bracket 1 by n1 square minus 1 by n2 square. So this is frequency nu. Now if this is frequency, then wavelength will be lambda is equals to 1 by frequency. So it will be just the reciprocal of this part. So 1 by lambda is equals to nu c by nu, so it will be nu by c, which is equals to mz square e to the power 4 divided by 8 epsilon naught square. In this part we have to add c, h cube 1 by n1 square minus 1 by n2 square. 1 by lambda is known as, this is known as wave number of waves per unit length. In the last equation, the quantity, that is this quantity over here, is constant. That is m is the power 4 divided by 8 epsilon naught square c h cube. This all the factors from this equation except for this z square. Okay, except for this factor, everything else is a constant and it is represented by r, known as Rydberg constant. So in this equation, in this particular equation, what we can write is 1 by lambda is equals to, in place of all the constant, I am replacing that with r. Z square is already there, so it will be 1 by n1 square minus 1 by n2 square. This is what we get. This is Bohr's formula for hydrogen-like atoms. For any other atoms, for any other atoms, then this Z will be replaced by the atomic number. For hydrogen-like atom, for hydrogen, Z is equals to 1. So 1 by lambda is equals to r 1 by n1 square minus 1 by n2 square. This is what we get. So now the energy, if you replace, now what I've told you is r is, the value of r is m e to the power 4 divided by 8 epsilon naught square c h cube. This is the value of r. Now in this particular equation, that is the equation of E. Suppose for all the constants, I replace the value of r. So the equation of E from equation number 4 was minus mz square e to the power 4 divided by 8 epsilon naught square h square 1 by n square. In this place, if I replace this constant, that is over here m e to the power 4 8 epsilon naught square h square, if you replace this, then we can write r. So E becomes minus, z is there, r, since this is h cube, over here h is only there, so we have to add one h. Since there is no c at this equation, so we have to also write c divided by n square. This is the equation of energy in terms of Rydberg constant. Now putting the value of r, because it is a constant, h is also a constant and c is also a constant. If you put the values of constant, E becomes minus z square 13.6 divided by n square electron volt. And for hydrogen-like atom, where z is equals to 1, E becomes minus rhc divided by n square, or minus 13.6 n square electron volt. So this is the energy of an electron of a hydrogen-like atom. So it's quite a long derivation, but it has got part and section. So please do write in your notebook in making different subtopics. Okay, if you have any doubt, please do ask me. And this much for today. Will continue in the next class. Thank you.